Okay, so in this lecture we're going to derive the equations of motion and begin the derivation. This is going to proceed throughout the next few lectures, but we'll start it here. This comes from solving the time derivative of the velocity vector with time and the equation related to that. And as we covered last time, following the motion, the rate of change of some quantity, in this case it'll be the velocity vector, is the local derivative plus the advection terms here. And expanding that out, the advection terms into their components, you see there's a u, a v, and a w component, meaning there's advection of material blowing in from the west, from the north and south direction, and vertically. And so what we're dealing with here is the velocity vector. So we're concerned about how the rate of change of velocity changes. And the way we have it in the second equation is at a fixed, following the motion. If we rearrange that, we can get at a fixed point on the left-hand side, and then bringing everything else to the right-hand side, we got the other terms. The third equation is the one we work with in the equations of motion, because in weather prediction, we're interested in how weather changes at a fixed point, at some location, maybe San Jose, Boulder, any place you're interested in. We want to know what the weather is, how it's going to change at that point. So we cast the equation in terms of solving the local rate of changes, and then having the advection and the total derivative on the right-hand side. So proceeding forward, we want to see what we're going to do about calculating what is the rate of change of velocity following the motion. Okay, so let's move forward from here. Okay, Newton's second law is the basis for the change in velocity with time following the motion. The acceleration is due to the summation of forces acting on an object. In this case, the object of interest is a parcel. And following the motion, we want to know what the net forces are on it to see if the parcel accelerates. So you have all seen Newton's second law as the net force acting on an object is equal to the mass times its acceleration. Acceleration, remember, is the time rate of change of velocity, again, following the motion. So if we rearrange this equation, the rate of change of velocity with time, the rate of change of momentum per unit mass, is the force per unit mass on the object. So that just plugs into the right-hand side of the momentum equation we put on the previous slide, and then we get to the third equation here, which is the rate of change in velocity with time at a fixed point is the advection terms plus the forces per unit mass acting on the parcel following the motion. Okay, so let's proceed from here and see what we're going to do about quantifying all these forces that could possibly act on a parcel. Okay, so to start off with, we're going to talk about two forces, the pressure gradient force and gravity. Okay, in the lecture notes that were handed out, I go through a detailed derivation of the pressure gradient force. You can refer to that for details, but the end result is that the force per unit mass due to the pressure gradient, meaning the change in pressure in space, the gradient of pressure in the field around the object, would move the object in a certain direction. And we know that if we have high to low pressure, the parcel is going to move in the direction of high to low pressure. That's something you learned from Met 60. The equation for the pressure gradient force is 1 over rho grad P. Expanding out grad P, dp dx, and that's the x component, dp dy, the y component, dp dz, the z component. These are local changes. So I'll make a diagram of this in the next slide, but for now, this is just the equation. We just want to know what the gradient of pressure is, and the flow is accelerated down the gradient in the direction of minus grad P, and then it's a 1 over rho leading that. Okay, so we just go ahead and plug that into one of the forces per unit mass that could possibly act on the parcel from the previous slide. So the velocity equation, momentum equation is dv dt, advection terms, pressure gradient, and now we throw in gravity, which only works in the vertical. So we put this little k hat there because that's the unit vector in the vertical. So now we have two of the forces that would be tacked on to the momentum equation describing how motion accelerates following parcels. Okay, there will be other terms that we'll put, and we'll get to those. Now expanding out the equation into its three components. And now we have a U momentum equation, a V momentum equation, and a W momentum equation. And you can see that taking the velocity vector and breaking it up into its three components on all of the terms here, you see what is the starting point of our three equations of motion for U west-east velocity, U, north-south velocity, V, and vertical velocity, W. Notice we have a pressure gradient term in each of these that is aligned in the direction of the component that the equation corresponds to. For example, this is the U momentum equation is dp dx. The V momentum equation has dp dy. The W equation has dp dz. And then we tack on gravity in the vertical only, because gravity only works in the vertical. Okay, so this rather peculiar looking diagram is intended to explain the pressure gradient force. So the black squares are air parcels, and I've shown two because I want to indicate the effect of the pressure gradient force on both. On the top here, you see P naught and P naught minus delta P. So on the left, the pressure may be P naught. On the right, the pressure may be P naught minus delta P. So the pressure is higher on the left than it is to the right. And that means there's a pressure gradient force, a pressure gradient that is, going from high to low, from left to right across the screen. And we indicate that on the bottom there. And the pressure gradient is minus grad P. Remember, we always describe the pressure gradient as minus the gradient of pressure because wind flows from high to low pressure. So we got a pressure gradient there, and you also see to either side of the boxes, the black boxes, we got these four arrows shooting off in each direction. That's the pressure field. So remember about pressure is that it's isotropic, meaning that pressure is exerted in equal amounts at a point in all directions around the point. So pressure doesn't have a direction. It just shoots out in all directions around the point. But if the pressure field is such that the pressure is higher to the left than on the right, as you see here, that means the pressure is decreasing as you go to the right, and therefore the force applied by the pressure on the box changes as you go left to right across the screen. So you see that, for example, on the left-hand box, the left face of the left-hand black box experiences a bigger pressure exerted on it than the pressure exerted on the right face, because the pressure on the left is higher than the pressure on the right of the box. Likewise on the box, the black box on the right, the pressure on the left side of the face is higher than on the right side of the face. So that means the box is experiencing a net force due to pressure that is higher on the left side of the box than on the right side of the box. Therefore, the pressure gradient force is going to push the box from left to right. There is a pressure gradient force exerted on the box because of the changing pressure across the field. Likewise, on the right side, you see the same thing. There's a higher pressure on the left box side of the box than on the right side, and therefore everything should move likewise. So you would, in this situation, you would expect to see these boxes move in that direction, not curved like that. I'm just not very good at using the equipment here, but there should be a pressure gradient from high to low moving these boxes to the right. That's how the pressure gradient force works.